The concept of nothing has puzzled and intrigued thinkers for centuries. Philosophers and scientists alike have grappled with the notion of a void, a space where nothing exists. This idea seems simple, yet it becomes profoundly complex when we attempt to define it. What does it mean for there to be nothing? Is there such a state where absolutely nothing exists, or does nothing have its own subtle existence, a kind of background from which something might emerge? Along with this, it is often said that the universe started from nothing, but then the biggest question emerges: where did nothing come from? In order to answer these questions, we first need to go back to ancient times. You see, in ancient times, the Greek philosopher Aristotle approached the idea of nothingness with caution. Aristotle believed that nature abhors a vacuum, a notion often summarized by the phrase horror vacui. He argued that a complete void could not exist because, without anything to contain or define it, the concept itself would be meaningless. To Aristotle, space was always filled with some form of substance, even if it was not immediately apparent. He viewed the idea of absolute emptiness as not just impossible but incoherent. This perspective dominated Western thought for many centuries, shaping how people understood the nature of existence and the fabric of the universe. As time passed and scientific inquiry advanced, the question of what nothing could be took on new dimensions. In the 20th century, with the rise of modern physics, the concept of empty space or vacuum became a hotly debated topic. Physicists like Paul Dirac, who contributed significantly to the field of quantum mechanics, started to explore the idea that even a vacuum, the seemingly empty space, was far from being truly nothing. Dirac proposed that a vacuum might actually be filled with particles and antiparticles that pop in and out of existence, a notion that suggested even empty space has a kind of structure, an underlying activity that defies the traditional idea of a void. This idea radically shifted the understanding of nothingness. In modern physics, a vacuum is not an absolute absence of matter or energy, but rather a space where particles might be momentarily absent, or where quantum fluctuations are constantly occurring. The vacuum, in this sense, is a seething background of potential, a place where particles and antiparticles can spontaneously appear and annihilate each other, creating an environment that is far from empty. This redefinition of nothingness plays a crucial role in our understanding of how the universe could arise from such a state. Against this backdrop, the Big Bang Theory emerges as our best explanation for the origin of the universe. In the early 20th century, scientists began to gather evidence that the universe was not static but rather expanding. This revelation set the stage for one of the most profound shifts in our understanding of the cosmos. The Big Bang Theory was first proposed by Belgian physicist Georges Lemaitre in 1927. Lemaitre, who was both a scientist and a Catholic priest, suggested that the universe began from a single incredibly dense point, which he referred to as the primeval atom, or cosmic egg. According to Lemaitre, this point contained all the matter and energy of the universe, and it began to expand and cool, eventually leading to the formation of galaxies, stars, and planets. 2 years later, in 1929, astronomer Edwin Hubble made a groundbreaking discovery that provided key evidence for Lemaitre's theory. Hubble observed that distant galaxies were moving away from us, and the farther they were, the faster they seemed to be receding. This observation implied that the universe was expanding, and if the galaxies were moving apart now, then at some point in the past, they must have been much closer together. Hubble's work gave substantial support to the idea that the universe had a beginning, a moment when it emerged from an incredibly hot and dense state. The Big Bang Theory fundamentally altered our understanding of the universe's origins. Instead of being eternal and unchanging, as many had previously thought, the universe was now seen as dynamic, evolving over time from a specific starting point. This theory also raised profound questions about what existed before the Big Bang, or whether such a concept as before even makes sense when discussing the beginning of time and space itself. What makes the Big Bang Theory particularly compelling is how it connects to the concept of nothingness. If the universe started from a singular point, a point where the density of matter and energy was infinitely high, then what existed before this event? Here, the philosophical and scientific definitions of nothingness intersect once again. Some theories suggest that the universe could have emerged from a quantum vacuum, a state where nothing in the traditional sense still contains the potential for creation due to the inherent fluctuations predicted by quantum mechanics. In this context, nothing is not truly empty, but is instead a fertile ground from which the universe could spring into existence. The very fabric of space and time might have been born from these quantum fluctuations, a process that aligns with both the philosophical musings of ancient thinkers and the modern scientific understanding of the vacuum. Thus, the question of how our universe started from nothing is intertwined with our evolving understanding of what nothing really means. The Big Bang Theory, supported by the discovery of the expanding universe, provides a framework within which we can explore this mystery. It suggests that the universe we know, with all its galaxies, stars, and planets, began from a state that might seem like nothing to us. A state without form, matter, or structure, but one that was rich with the potential for everything to emerge. What was before the Bang? As we journey further into understanding the origins of our universe, we come face to face with one of the most enigmatic concepts in modern cosmology, the singularity at the heart of the Big Bang. This singularity is often described as the point from which all space, time, and matter originated. However, what exactly is a singularity? And what does it tell us about the moment before the Big Bang? In simple terms, a singularity is a point in space-time where the density of matter and the curvature of space become infinite. It is a region where our current understanding of the laws of physics no longer applies, where the equations that govern the behavior of the universe break down. This breakdown occurs because the values involved, such as gravitational forces and density, become so extreme that our mathematical models can no longer describe what is happening. This makes the singularity not just a physical concept, but also a boundary in our understanding. The singularity at the start of the Big Bang is particularly perplexing because it represents a moment when the universe was compressed into an infinitesimally small, infinitely dense point. At this point, all known laws of physics, including general relativity, cease to function as they normally do. This leads to profound questions. What was before the singularity? What caused the Big Bang? And can we ever truly understand what happened in that first moment? In the 1970s, physicists Stephen Hawking and Roger Penrose made significant strides in exploring the nature of singularities. Their work, which combined Einstein's theory of general relativity with quantum mechanics, provided new insights into how singularities could exist not just at the heart of black holes, but also as the starting point of our universe. Hawking and Penrose showed that under certain conditions, such as the immense gravitational forces at play during the Big Bang or within black holes, singularities are not just theoretical possibilities, but inevitable outcomes. Hawking and Penrose's research indicated that if we trace the history of the universe backward in time, we inevitably reach a point where the universe was so dense that space and time themselves become infinitely curved. This is the singularity at the Big Bang, a point where our conventional understanding of space, time, and matter collapses. At this singularity, all the matter in the universe is thought to have been compressed into an incredibly small, hot, and dense state before expanding rapidly in what we now call the Big Bang. But what was before the Big Bang? This question challenges the very nature of time itself. In our everyday experience, time is a continuous flow. One moment leads to the next, and we can always ask what happened before. However, when it comes to the singularity, this straightforward concept of time breaks down. Some physicists suggest that time itself may have started at the moment of the Big Bang, meaning that asking what came before is akin to asking what lies north of the North Pole. In this view, there simply was no before because time did not exist. Other theories suggest that the singularity might have emerged from a pre-existing state, possibly involving quantum fluctuations in a vacuum or even from a previous universe. These ideas are speculative, as they push the boundaries of current scientific understanding. Nonetheless, they offer intriguing possibilities for what might lie beyond the observable universe and its history. One of the most fascinating aspects of Hawking's work was his exploration of black holes, which are often described as the cousins of the Big Bang singularity. Black holes are regions in space where gravity is so strong that nothing, not even light, can escape. At the core of a black hole is believed to be a singularity similar to that of the Big Bang, a point where matter is crushed to infinite density, and the known laws of physics cannot describe the conditions. Hawking's research into black holes led to some surprising conclusions. He discovered that black holes are not entirely black, but emit radiation, now known as Hawking radiation. This finding suggested that black holes could eventually evaporate over time, challenging the notion that information swallowed by a black hole is lost forever. This idea has profound implications for our understanding of singularities and the ultimate fate of the universe. The connection between black holes and the Big Bang singularity is not just a matter of similarity. The study of black holes provides a kind of laboratory for understanding the extreme conditions that existed at the beginning of the universe. By studying how singularities form and behave within black holes, scientists hope to gain insights into the nature of the Big Bang itself. Yet despite these advances, the singularity remains one of the greatest mysteries in cosmology. It represents a point where our current theories, whether of relativity or quantum mechanics, are insufficient to fully describe the reality of what happened. This is why the singularity is often referred to as a breakdown in the laws of physics. It is a place where our knowledge reaches its limits and where new theories or ideas are needed to make further progress. Some physicists believe that a theory of quantum gravity, which would unify general relativity with quantum mechanics, might provide the answers we seek. Such a theory could potentially describe what happens at the singularity and, by extension, what might have come before the Big Bang. However, despite much theoretical work, a complete and experimentally verified theory of quantum gravity remains elusive. The singularity at the start of the Big Bang, therefore, stands as both a beginning and a boundary, a starting point for the universe as we know it, and a limit to our current understanding. It challenges us to think beyond our everyday experience of time, space, and matter, to consider what might lie beyond the observable universe and the laws that govern it. In our quest to understand the origins of the universe, we find ourselves returning to the profound questions that have puzzled thinkers for millennia. What is the nature of existence? How did everything come from nothing? And can we ever truly grasp the moment when time, space, and matter first emerged from the singularity? These questions remain at the forefront of our search for knowledge as we continue to explore the deepest mysteries of the cosmos. Quantum fluctuations, the seeds of something. As we delve deeper into the mysteries of the universe's beginnings, we encounter the strange and counterintuitive world of quantum mechanics, where the concept of nothing takes on a whole new meaning. One of the most intriguing ideas in this realm is that even what we think of as empty space is not truly empty. Instead, it's a seething, restless place filled with potential. This concept, central to our understanding of quantum mechanics, introduces the idea of quantum fluctuations, tiny, random changes in energy that occur in the vacuum of space. These fluctuations, though seemingly insignificant, may hold the key to how something can emerge from nothing. The discovery that empty space isn't truly empty was a pivotal moment in modern physics, one that began to take shape in the mid-20th century. In 1947, two Dutch physicists, Hendrik Casimir and Dirk Polder, conducted an experiment that provided the first direct evidence of these quantum fluctuations. They observed what is now known as the Casimir effect, which demonstrated that two uncharged parallel metal plates placed very close together in a vacuum could experience an attractive force between them. This force was not due to any conventional electromagnetic interaction, but rather to the presence of quantum fluctuations in the vacuum between the plates. The Casimir effect is a fascinating phenomenon because it shows that even in a vacuum, what we might traditionally consider as nothing, there is still something happening. These fluctuations in the vacuum are the result of the uncertainty principle, a cornerstone of quantum mechanics formulated by Werner Heisenberg. The uncertainty principle states that it's impossible to know both the exact position and the exact momentum of a particle simultaneously. As a consequence, particles and their corresponding fields can't ever be completely still or completely absent, even in a vacuum. Instead, they constantly fluctuate in and out of existence, giving rise to these tiny, random changes in energy that we call quantum fluctuations. But what does this mean for the origins of the universe? The idea that quantum fluctuations can give rise to something from nothing might sound strange, but it's a key concept in quantum field theory. In this framework, the vacuum is not a simple void, but rather a complex, dynamic state filled with potential energy. This energy can sometimes manifest as particles that appear and disappear so quickly that they are often called virtual particles. These particles don't exist in the usual sense. They don't have a lasting presence, but they do exist briefly enough to have real effects, as seen in the Casimir effect. Quantum field theory suggests that these fluctuations can be incredibly powerful on a microscopic scale. Over time, and under the right conditions, these tiny fluctuations could have significant effects. For instance, it's possible that in the extremely high-energy environment of the early universe, just after the Big Bang, these quantum fluctuations could have played a crucial role in shaping the structure of the cosmos. The idea is that these fluctuations could serve as the seeds for the formation of galaxies, stars, and other large-scale structures we observe in the universe today. This concept is supported by the theory of cosmic inflation, which posits that the universe underwent a rapid and exponential expansion just fractions of a second after the Big Bang. During this inflationary period, quantum fluctuations would have been stretched across vast distances, imprinting tiny variations in the density of the universe. These variations, though incredibly small, provided the initial irregularities that gravity could later amplify into the galaxies, clusters, and cosmic web that fill our universe. In this way, quantum fluctuations provide a mechanism by which the universe could have transitioned from a nearly uniform state to the richly structured cosmos we observe today. They illustrate how the tiniest, most random events at the quantum level can have profound consequences on a cosmic scale. But quantum fluctuations also hint at a more profound idea, that the universe itself might have arisen from such a fluctuation. Some theories propose that in the quantum vacuum, a fluctuation could have occurred that set off the chain of events leading to the Big Bang. In this view, the universe didn't require a pre-existing state of something to come into being. Instead, it could have emerged from nothing, or more precisely, from the quantum vacuum, which, as we've seen, is far from empty. This concept challenges our classical notions of cause and effect, of creation and existence. It suggests that the universe doesn't need a cause in the traditional sense because the quantum vacuum itself is a place where the laws of physics allow for spontaneous creation. It's a realm where particles can pop in and out of existence, and where, under the right conditions, entire universes might even come into being. This idea is still the subject of much debate and research, and it's important to note that while quantum field theory and the concept of quantum fluctuations provide a framework for understanding how the universe could arise from nothing, many details remain unresolved. The exact mechanisms by which such a fluctuation could lead to the universe we observe today are complex and not yet fully understood. Nevertheless, the idea that our universe could have emerged from a quantum fluctuation offers a tantalizing glimpse into the profound and often perplexing nature of reality. As we consider these ideas, we find ourselves once again returning to the question that has haunted thinkers for centuries. How can something come from nothing? Quantum mechanics, with its strange and often counterintuitive principles, offers one possible answer. It suggests that nothing is not a barren emptiness, but a fertile ground of possibilities, where the seeds of something, the seeds of everything, are always present, just waiting for the right conditions to take root. In this sense, the story of our universe's origins is not just about a single moment in time, but about the ongoing dance of creation and destruction that takes place in the quantum vacuum. It's a story where the tiniest fluctuations can lead to the birth of stars and galaxies, and where the boundaries between nothing and something are not as clear-cut as they might seem. The rapid expansion. In the unfolding story of our universe's origins, one of the most intriguing and essential chapters is the idea of cosmic inflation. This theory, first proposed by physicist Alan Guth in 1980, suggests that the universe underwent an incredibly rapid expansion just fractions of a second after the Big Bang. This brief but intense period of inflation holds the key to understanding many of the mysteries that puzzled cosmologists for decades. To grasp the significance of cosmic inflation, it's important to understand the state of the universe just after the Big Bang. In those earliest moments, the universe was a hot, dense soup of particles, all packed together in an unimaginably small space. As the universe began to expand and cool, these particles started to combine, eventually leading to the formation of the matter that makes up everything we see today. But this simple picture left many questions unanswered, and as scientists dug deeper, they encountered several problems that didn't quite fit with the standard Big Bang model. One of the most pressing issues was known as the horizon problem. This problem arises when we consider the uniformity of the cosmic microwave background, CMB radiation, the faint afterglow of the Big Bang that permeates the universe. The CMB is remarkably consistent in temperature across vast distances, even in regions of the sky that, according to the standard model, should never have been able to exchange information or energy. In other words, these regions are so far apart that light from one side of the universe hasn't had time to reach the other side, given the universe's age. Yet they have nearly identical temperatures, as if they had somehow been in contact with each other. The standard Big Bang theory couldn't adequately explain this uniformity. It suggested that regions of the universe that are now far apart were also far apart from the very beginning, making it difficult to understand how they could have come to such a close thermal equilibrium. This paradox hinted at something missing from the standard model, an aspect of the universe's early history that had not yet been accounted for. Then came Alan Guth's revolutionary proposal: cosmic inflation. Guth suggested that during the very first fraction of a second after the Big Bang, between 10 circumflex 36 and 10 circumflex 32 seconds, the universe expanded at an exponential rate. This expansion was much faster than the speed of light, though it's important to note that this doesn't violate any physical laws because it's space itself that was expanding, carrying matter along with it. This period of rapid inflation would have stretched out any initial irregularities in the universe to such an extent that the observable universe today appears remarkably uniform. In other words, regions that are now vastly separated were once much closer together before inflation, allowing them to come into thermal equilibrium. When inflation occurred, it expanded these regions far beyond the distances we observe today, thus resolving the horizon problem. Cosmic inflation also addressed another major issue in cosmology: the flatness problem. The flatness problem arises when we consider the geometry of the universe. According to general relativity, the universe can have one of three shapes. It can be flat, like a piece of paper, closed, like the surface of a sphere, or open, like a saddle. Observations show that the universe is remarkably flat, meaning the density of matter and energy is very close to the critical value needed to stop the universe from collapsing in on itself or expanding forever at an accelerated rate. But why should the universe be flat? Any small deviation from flatness in the early universe would have led to a drastically different universe today, either one that collapsed in on itself shortly after the Big Bang, or one that expanded so rapidly that galaxies and stars could never have formed. The standard Big Bang model couldn't easily explain why the universe started out so finely tuned to be flat. Here again, cosmic inflation provided an elegant solution. During inflation, the rapid expansion of space would have effectively flattened out any curvature, much like how the surface of a balloon appears flatter as it is blown up. This means that even if the universe had started with some curvature, inflation would have stretched it so much that any deviation from flatness would become virtually undetectable, giving us the flat universe we observe today. Inflation theory didn't just solve these two problems, it also made several predictions that have since been confirmed by observations. For instance, inflation predicts that the universe should have slight fluctuations in density, leading to the formation of galaxies and large-scale structures. These fluctuations are thought to arise from quantum fluctuations during inflation, which were stretched to cosmic scales as space expanded. These tiny variations in density eventually grew under the influence of gravity, seeding the formation of galaxies, stars, and everything else we see in the universe. When scientists looked at the cosmic microwave background radiation, they found exactly these kinds of fluctuations, small variations in temperature that correspond to slight differences in density. The discovery of these fluctuations provided strong evidence in favor of the inflationary model and has helped solidify its place as a central piece of our understanding of the early universe. While cosmic inflation answers many of the questions that the standard Big Bang theory could not, it also raises new ones. One of the biggest mysteries is what caused inflation to start and stop. Guth's original proposal was that inflation was driven by a hypothetical field called the inflaton field, which had a certain kind of potential energy that caused space to expand rapidly. As the universe inflated, this potential energy would eventually be released, converting into particles and radiation, and ending the inflationary period. However, the exact nature of the inflaton field remains unknown. While many theories have been proposed, it's still unclear what the field might be or how it operated. Additionally, some versions of inflation theory suggest that inflation might not have ended everywhere in the universe. Instead, in some regions, inflation could continue indefinitely, leading to the idea of a multiverse, a collection of many universes, each with its own physical properties and laws. Space-time fabric, the birth of dimensions. The origins of our universe are deeply intertwined with the concepts of space and time, two fundamental aspects of reality that seem so intrinsic to our experience that we often take them for granted. Yet, our understanding of space and time and how they came into existence underwent a profound transformation in the early 20th century, thanks to Albert Einstein's groundbreaking work. His theory of general relativity, published in 1915, revolutionized the way we think about these concepts, revealing that space and time are not merely passive backgrounds against which events occur, but are dynamic entities that play an active role in shaping the universe. Before Einstein, space and time were generally thought of as absolute and unchanging. This view, rooted in the work of Isaac Newton, suggested that space was a vast, unchanging stage where the events of the universe played out, and time was a uniform flow that ticked away steadily, independent of anything else. This classical view worked well for many situations, but it had limitations, especially when dealing with extremely large or small scales, or with the immense gravitational forces found near massive objects like stars or black holes. Einstein's theory of general relativity introduced a radically different perspective. He proposed that space and time are actually part of a single interconnected fabric known as spacetime. In this framework, space and time are not separate entities, but are interwoven into a four-dimensional continuum where events occur. This spacetime fabric is not static. It can be stretched, compressed, and curved by the presence of mass and energy. Essentially, Einstein showed that what we perceive as the force of gravity is actually the result of this curvature of spacetime caused by massive objects. One of the most striking implications of Einstein's theory is that the very existence of space and time as we understand them is a result of the Big Bang. In the earliest moments of the universe, when the singularity was still present, the concepts of space and time as we know them may not have existed. As the universe expanded from the singularity during the Big Bang, so too did space and time emerge and begin to take shape. To visualize this, imagine the surface of a balloon. As the balloon inflates, its surface expands, creating more and more space on which objects can exist. Similarly, the expansion of the universe can be thought of as the stretching of the space-time fabric, with the Big Bang acting as the moment when this expansion began. Before this expansion, there was no space in the conventional sense, and time as we understand it didn't exist either. It was the Big Bang that brought space and time into existence, along with all the matter and energy in the universe. Einstein's theory also explains how the presence of mass and energy affects this fabric. According to general relativity, massive objects like stars and planets cause the spacetime around them to curve. This curvature is what we perceive as gravity. Objects moving through space-time follow the curves created by these massive bodies, which is why planets orbit stars and why we feel the pull of gravity on Earth. The more massive an object, the more it warps the space-time around it, creating a deeper well in the fabric. This is why black holes, which are incredibly dense and massive, create such extreme curvature that not even light can escape from them. The idea that space and time are dynamic and responsive to the presence of matter and energy has profound implications for our understanding of the universe. It means that the structure of the universe is not fixed but constantly changing in response to the distribution of matter and energy within it. This dynamic nature of space-time is what allows for the possibility of phenomena like gravitational waves, ripples in the space-time fabric caused by violent cosmic events such as the collision of black holes. Gravitational waves were first predicted by Einstein as a consequence of his theory of general relativity, but they were not directly observed until 2015, a century after Einstein published his theory. The detection of these waves confirmed that space-time is indeed a flexible, responsive entity that can be stretched and compressed by the movement of massive objects. This discovery opened up a new way of observing the universe, providing a way to study cosmic events that are otherwise invisible, like black hole mergers and neutron-star collisions. But the idea that space and time are linked and can be influenced by mass and energy also leads us back to the Big Bang and the question of how these dimensions first came into being. If space-time was born in the Big Bang, then the expansion of the universe is essentially the stretching of this space-time fabric from a highly concentrated, dense state into the vast, ever-expanding universe we observe today. Einstein's theory helps us understand not only how space and time emerged, but also how they continue to evolve. The universe's expansion, which we observe through the redshift of distant galaxies, is a sign that the space-time fabric is still stretching, carrying galaxies along with it. This expansion is not just the movement of galaxies through space, but the expansion of space itself. This ongoing expansion raises questions about the ultimate fate of the universe. Will the expansion continue forever, causing the universe to grow increasingly cold and empty? Or will it eventually reverse, leading to a collapse back into a singularity in a big crunch? Or could it even lead to something else entirely, like a big rip, where the expansion becomes so rapid that space-time itself tears apart? These questions remain open, but what is clear is that the fabric of space-time is at the heart of whatever happens next. It is the stage upon which the drama of the universe unfolds, a stage that is itself an active participant in the story. Einstein's theory of general relativity has provided us with a powerful tool for understanding the universe, one that has withstood the test of time and been confirmed by numerous observations and experiments. It has shown us that space and time are not mere backdrops to the events of the universe, but are integral to the very nature of reality. From the birth of the universe in the Big Bang, to the formation of stars and galaxies, and even to the bending of light around massive objects, the fabric of space-time is woven into the fabric of existence itself. The role of dark matter and dark energy. As we deepen our understanding of the cosmos, we encounter forces that, though invisible and elusive, play a crucial role in shaping the universe as we know it. These are the enigmatic entities known as dark matter and dark energy, two of the most mysterious components of the universe that continue to challenge and intrigue scientists. The story of dark matter begins in the early 20th century, with observations that hinted at something unseen influencing the behavior of galaxies. In 1933, Swiss astronomer Fritz Zwicky was studying the Coma cluster, a large group of galaxies located millions of light-years from Earth. Zwicky noticed something strange. The galaxies in the cluster were moving much faster than expected based on the visible matter, the stars and gas, contained within them. According to the laws of physics, specifically Newton's law of gravitation, the observed amount of visible matter was not nearly enough to account for the gravitational forces required to keep these galaxies bound together. They should have been flying apart, yet they remained intact. Zwicky proposed that there must be some unseen or dark matter providing the additional gravitational pull needed to hold the cluster together. He called this unknown substance dunkle materie, or dark matter. Although his idea was initially met with skepticism, it planted the seed for what would become one of the most significant concepts in cosmology. Over the following decades, more evidence emerged that dark matter must exist. In the 1970s, astronomer Vera Rubin provided crucial support for the dark matter hypothesis through her observations of the rotation curves of galaxies. Rubin discovered that the outer regions of galaxies were rotating at the same speed as the inner regions, which contradicted the predictions of Newtonian dynamics. If only visible matter were present, the outer stars in a galaxy should rotate more slowly, much like planets in our solar system orbit the Sun. But Rubin's findings suggested that something unseen was exerting additional gravitational force, keeping the outer stars moving at the same speed as those closer to the center. These observations led to the conclusion that dark matter must make up a significant portion of the universe's total mass. Unlike ordinary matter, which interacts with light and can be seen, dark matter does not emit, absorb, or reflect any electromagnetic radiation, making it completely invisible. Its presence is inferred only through its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Today, dark matter is believed to constitute about 27% of the universe's total mass and energy content, while ordinary matter, everything we can see, touch, and measure, makes up only about 5%. Despite its abundance, the true nature of dark matter remains one of the biggest mysteries in astrophysics. Scientists have proposed various candidates for dark matter, including weakly interacting massive particles, WIMPs, and axions. But so far, these particles have eluded direct detection. Experiments continue around the world, deep underground and in space, in the hopes of capturing evidence of dark matter particles, but the mystery remains unsolved. While dark matter exerts a pull on the universe, another, even more mysterious force appears to be pushing it apart. This force is known as dark energy, and its discovery in the late 20th century added a new twist to our understanding of the cosmos. In the 1990s, two independent teams of astronomers, one led by Saul Perlmutter and the other by Adam Rees and Brian Schmidt, were studying distant supernovae, exploding stars that can serve as standard candles to measure cosmic distances. They expected to find that the expansion of the universe, set in motion by the Big Bang, was gradually slowing down due to the gravitational pull of all the matter in the universe. However, their observations revealed something completely unexpected. The universe's expansion was not slowing down, but accelerating. This discovery was shocking because it suggested that some unknown force was counteracting gravity and causing the expansion of the universe to speed up. This force was dubbed dark energy, and it quickly became a central focus of cosmological research. Unlike dark matter, which pulls matter together through gravity, dark energy appears to work in the opposite direction, driving the universe apart. The nature of dark energy is even more mysterious than that of dark matter. It is thought to make up about 68% of the universe's total mass energy content, meaning that it dominates the cosmic landscape. One possible explanation for dark energy is the cosmological constant, a concept first introduced by Einstein as a term in his equations of general relativity. Einstein originally included the cosmological constant to allow for a static universe, which was the prevailing belief at the time. However, when it was later discovered that the universe is expanding, Einstein reportedly called the cosmological constant his biggest blunder and removed it from his equations. Ironically, the discovery of the accelerating universe suggests that the cosmological constant might actually describe a real force, dark energy. According to this idea, dark energy is a property of space itself, a kind of energy inherent in the fabric of space-time that drives the accelerated expansion of the universe. However, other theories suggest that dark energy might not be constant at all, but could vary over time, or that it might be the result of some new, as yet undiscovered field or force. The discovery of dark energy has profound implications for the fate of the universe. If the acceleration continues indefinitely, the universe could expand forever, becoming increasingly cold, dark, and empty as galaxies move farther apart and stars burn out. This scenario is often referred to as the Big Freeze. Alternatively, if dark energy were to change in strength over time, it could lead to other outcomes, such as a Big Rip, where the expansion becomes so extreme that it eventually tears apart galaxies, stars, planets, and even atomic structures. Dark matter and dark energy together make up about 95% of the universe, leaving ordinary matter, the stars, planets, and galaxies that we can see and measure, as just a small fraction of the cosmic pie. Yet, despite their dominance, these dark components remain some of the least understood aspects of the universe. They challenge our understanding of the fundamental nature of reality and drive much of the current research in cosmology. Cosmic background radiation, the echo of the Big Bang. Cosmic microwave background radiation is a subtle yet pervasive afterglow from the birth of the universe. Discovered in 1965 by Arno Penzias and Robert Wilson, this radiation provided some of the most compelling evidence for the Big Bang theory and has since become a cornerstone in our understanding of the cosmos. The story of the cosmic microwave background radiation, or CMB, begins with the Big Bang itself. According to the Big Bang theory, the universe began as an incredibly hot and dense point, filled with energy and particles in a chaotic, high-energy state. As the universe expanded, it also cooled, allowing particles to combine and form the first atoms. This process, known as recombination, occurred roughly 380,000 years after the Big Bang. Before recombination, the universe was opaque, filled with a hot plasma of free electrons and protons that scattered photons, or light particles, in all directions. However, as the universe cooled and the electrons combined with protons to form neutral hydrogen atoms, photons were able to travel freely through space for the first time. This release of photons marks the decoupling of matter and radiation and is the moment when the universe became transparent. The light from this era has been traveling through space ever since, gradually losing energy as the universe continues to expand and cool. Today, we observe this ancient light as the CMB, a faint glow that fills the entire sky. The CMB is not just any ordinary light, it is the oldest light in the universe, a direct remnant from the time when the universe first became transparent. It provides a snapshot of the universe as it was just 380,000 years after the Big Bang, offering a unique window into the conditions of the early cosmos. The discovery of the CMB by Penzias and Wilson was, in many ways, a happy accident. The two physicists were working at Bell Labs in New Jersey using a large horn antenna designed for satellite communications. They noticed a persistent noise in their data, a background hiss that seemed to come from all directions in the sky. This noise was present no matter where they pointed their antenna, and it didn't seem to be coming from any specific source. At first, Penzias and Wilson suspected that the noise was due to interference from nearby cities or even pigeon droppings on the antenna. However, after meticulously cleaning the antenna and ruling out all possible sources of interference, they were left with the conclusion that this noise was something real, something cosmic. Unbeknownst to Penzias and Wilson, a group of physicists at nearby Princeton University, led by Robert Dicke, were also searching for evidence of the CMB. Dicke and his colleagues had predicted that if the Big Bang theory were correct, there should be a faint afterglow from the early universe, now cooled to just a few degrees above absolute zero and detectable as microwave radiation. When Penzias and Wilson learned of this work, they realized that the noise they had detected was, in fact, the cosmic microwave background radiation. The discovery of the CMB provided a powerful confirmation of the Big Bang theory. Prior to this discovery, there were competing theories about the origin of the universe, including the steady-state theory, which posited that the universe had no beginning and was in a constant state of creation and expansion. The CMB's existence, however, was a clear signal that the universe had indeed begun in a hot, dense state and had been expanding ever since. The CMB is remarkably uniform, with a temperature of approximately 2.7 degrees Kelvin, or just above absolute zero. This uniformity supports the idea that the early universe was in a state of near-perfect equilibrium, with matter and radiation evenly distributed throughout. However, the CMB also contains tiny fluctuations in temperature, differences of just a few millionths of a degree, known as anisotropies. These slight variations are incredibly important because they represent the seeds of all the structure we see in the universe today. These anisotropies are believed to be the result of quantum fluctuations in the early universe, which were stretched to cosmic scales during the period of inflation. Over time, these tiny density variations were amplified by gravity, leading to the formation of galaxies, stars, and clusters. The study of these fluctuations has allowed scientists to learn a great deal about the universe's age, composition, and even its eventual fate. In the decades following Penzias and Wilson's discovery, the study of the CMB has become one of the most important fields in cosmology. Several missions, such as NASA's Cosmic Background Explorer, COBE, in the 1990s and the Wilkinson Microwave Anisotropy Probe, WMAP, in the 2000s, have mapped the CMB with increasing precision. These missions have provided detailed images of the early universe, revealing the subtle patterns of anisotropies that tell the story of how the universe evolved from a smooth, featureless expanse into the richly structured cosmos we see today. Perhaps one of the most significant findings from the study of the CMB is the age of the universe. By analyzing the CMB, scientists have determined that the universe is approximately 13.8 billion years old. This age is consistent with other measurements, such as the rate of expansion of the universe known as the Hubble constant and the distribution of galaxies. The CMB also provides insights into the composition of the universe, indicating that it is made up of about 5% ordinary matter, 27% dark matter, and 68% dark energy. The discovery and study of the CMB have transformed our understanding of the universe's origins and its evolution. It serves as a direct link to the Big Bang, a time capsule that has carried the imprint of the early universe across billions of years and vast distances. Through the CMB, we can trace the history of the universe from its fiery beginnings to the formation of galaxies and beyond. The CMB is a humbling reminder of the power of scientific discovery. What began as an unexplained noise in an antenna led to a profound understanding of the cosmos, confirming the Big Bang theory and opening new avenues of inquiry into the nature of the universe. As we continue to study this ancient light, we are reminded of the vastness of the universe, the depth of its history, and the enduring mysteries that still await our exploration. Multiverse Theory. Are we alone? As we contemplate the vastness of the cosmos and the mysteries that still elude us, a question naturally arises. Is our universe the only one? Or could there be countless other universes, each with its own unique laws of physics, stars, and perhaps even life? This idea, known as the Multiverse Theory, pushes the boundaries of our understanding and challenges our very notion of reality. It suggests that the universe we observe is just one of many, possibly an infinite number, each existing in its own separate realm. The concept of the multiverse has its roots in several different areas of physics, but one of the earliest and most intriguing ideas comes from quantum mechanics, the branch of physics that deals with the behavior of particles on the smallest scales. In 1957, American physicist Hugh Everett proposed a radical interpretation of quantum mechanics that would later become known as the many worlds interpretation. According to Everett, every possible outcome of a quantum event actually occurs, but in separate parallel universes. In the world of quantum mechanics, particles can exist in multiple states simultaneously, a phenomenon known as superposition. For example, a particle can be in two different locations at once or spin in two directions simultaneously. When we observe or measure the particle, however, we only see it in one specific state. This process, known as collapse of the wave function, has puzzled physicists for decades. What happens to the other possible states that we don't observe? Do they simply vanish, or do they continue to exist in some form? Everett's many worlds interpretation suggests that rather than collapsing, the wave function splits into multiple branches, with each branch representing a different possible outcome. In this view, every time a quantum event occurs, the universe splits into multiple parallel versions, each following a different path. For instance, If a particle has a 50% chance of being in position A and a 50% chance of being in position B, then both outcomes occur but in different universes. In one universe, the particle is in position A, and in another, it's in position B. According to this theory, all possible outcomes of all quantum events are realized in some universe, leading to an infinite number of parallel universes. The many worlds interpretation is a striking and controversial idea, but it offers a way to resolve some of the paradoxes of quantum mechanics without the need for wave function collapse. It also implies that our universe is just one of an unimaginably vast number of parallel universes, each as real as our own, but forever inaccessible to us. While the many worlds interpretation of quantum mechanics presents one version of the multiverse concept, there is another intriguing idea that arises from cosmology and the study of the early universe. This is the inflationary multiverse, a theory that emerged from the work of physicists like Alan Guth and André Linde in the 1980s. As we've explored earlier, the theory of cosmic inflation suggests that in the first moments after the Big Bang, the universe underwent a brief but extremely rapid expansion. This inflationary period stretched spacetime on a scale that is difficult to imagine, smoothing out any initial irregularities and setting the stage for the formation of galaxies and other cosmic structures. But what if inflation didn't stop everywhere at once? What if it continued in some regions of space while stopping in others? André Linde proposed that inflation might be a never-ending process with different regions of space experiencing inflation at different times. In this model, our observable universe is just one bubble in a much larger, perhaps infinite sea of inflating space. Each bubble could represent a different universe with its own set of physical laws and constants. Some of these universes might be similar to ours, while others could be radically different, with different numbers of dimensions, different types of particles, and even different laws of physics. This idea is known as the inflationary multiverse or the bubble universe theory. According to this model, inflation is an eternal process that continually creates new universes, each emerging from its own region of inflating space. Our universe then is just one of many, one bubble among countless others. This notion of an infinite multiverse challenges our understanding of reality and suggests that what we perceive as the universe is just a tiny fragment of a much larger, more complex structure. The inflationary multiverse also offers an explanation for some of the fine-tuning observed in our universe. For example, certain physical constants, such as the strength of the electromagnetic force or the cosmological constant, appear to be finely tuned to values that allow for the existence of life. In a multiverse with an infinite number of universes, each with different physical constants, it's not surprising that at least one universe would have the right conditions for life. We happen to live in that universe because, in universes with different constants, life might not be possible. While the idea of a multiverse is fascinating, it also raises profound philosophical and scientific questions. Can we ever truly know if these other universes exist? If they do exist, how could we detect them or communicate with them? Some scientists argue that the multiverse is an untestable hypothesis, an idea that lies beyond the reach of observation and experimentation, and therefore beyond the scope of science as we currently understand it. However, others believe that the multiverse could leave subtle imprints on our universe that might one day be detectable. For example, collisions between our universe and other bubble universes could leave traces in the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills the universe. Detecting such imprints would provide evidence that our universe is indeed part of a larger multiverse. Despite the challenges in proving or disproving the multiverse theory, it has become a powerful and influential concept in modern physics and cosmology. It pushes the boundaries of what we consider possible and invites us to imagine a reality that is far more complex and varied than we ever thought possible. The idea of the multiverse also resonates with our deepest questions about existence. Are we alone in the universe? If the multiverse exists, then the answer is both yes and no. We may be alone in our own universe, but we are not alone in the larger multiverse. There could be countless other universes, each with its own version of reality, its own stars and planets, and perhaps even its own intelligent beings pondering their place in the cosmos. The multiverse theory challenges us to think beyond our own universe and to consider the possibility that the reality we know is just one small part of a much larger, more intricate tapestry. It is a concept that inspires wonder and curiosity, reminding us that the universe, or multiverse, is a vast and mysterious place, full of possibilities that we are only beginning to explore. Time's arrow, the flow from nothing to now. One aspect of our existence stands out as both fundamental and elusive: time. Time is woven into the fabric of our daily lives, guiding the rhythm of our existence, from the ticking of a clock to the aging of our bodies. Yet, despite its omnipresence, time remains one of the most profound and puzzling concepts in both science and philosophy. Perhaps the most intriguing feature of time is its apparent unidirectional flow, a concept famously referred to as time's arrow by the British astrophysicist Arthur Eddington in the 1920s. The idea of time's arrow captures the observation that time seems to move in one direction only, forward. We experience the past as something fixed and unchangeable, the present as the fleeting moment we live in, and the future as something that has yet to unfold. This progression from past to future is something we take for granted, but it raises deep questions about the nature of time itself. Why does time move forward and not backward? Is this flow of time an intrinsic feature of the universe, or is it a product of the way we perceive reality? Arthur Eddington introduced the concept of time's arrow to describe this directional quality of time. He noted that while the fundamental laws of physics, such as those governing motion and forces, do not inherently favor one direction of time over another, our experience of time is decidedly asymmetrical. For example, when we observe events like a glass falling off a table and shattering on the floor, we intuitively understand that this sequence of events happens in one direction. The reverse, a shattered glass reassembling itself and leaping back onto the table, violates our sense of reality, even though the laws of physics in their most basic forms do not explicitly prohibit it. To understand why time's arrow points in one direction, we must consider the concept of entropy, a measure of disorder or randomness in a system. Entropy is a central idea in the second law of thermodynamics, which states that in a closed system, the total entropy can never decrease over time. In other words, the natural progression of any isolated system is toward greater disorder. This tendency for entropy to increase gives time its arrow, providing a directionality that aligns with our everyday experiences. Imagine a simple example: a cup of hot coffee left on a table. Over time, the heat from the coffee will disperse into the surrounding air, causing the coffee to cool down. This process increases the entropy of the system as the energy, once concentrated in the hot coffee, spreads out and becomes more evenly distributed. We never see the reverse process occur spontaneously, a cup of coffee that cools down and then suddenly heats back up on its own, because this would imply a decrease in entropy, which is statistically improbable. Entropy, therefore, gives us a clue as to why we perceive time as moving forward. The universe, from the moment of the Big Bang, has been evolving from a state of low entropy to higher entropy. The early universe was hot, dense, and relatively uniform, a state of low entropy. As the universe expanded and cooled, it became more structured, with galaxies, stars, and planets forming from the initial chaos. However, as these structures formed, the overall entropy of the universe continued to increase, driven by processes such as the burning of stars and the mixing of gases in galaxies. This increase in entropy over time is what we experience as the forward flow of time. The past represents a state of lower entropy, the present is a point along the trajectory of increasing entropy, and the future holds even greater entropy. The arrow of time, therefore, is not just a feature of our perception, but a fundamental aspect of the universe's evolution. Yet this understanding of time's arrow raises additional questions. If time is tied to entropy, does this mean that time could theoretically reverse if entropy were to decrease? And what does this imply about the ultimate fate of the universe? Some physicists have speculated that if the universe were to eventually reach a state of maximum entropy, often referred to as heat death, where all energy is evenly distributed and no work can be done, time itself might lose its directionality. In such a state, there would be no observable difference between past, present, and future because no further change or increase in entropy would be possible. This idea suggests that time's arrow is intrinsically linked to the dynamism of the universe, the constant flux and flow of energy and matter that drives change. The concept of time's arrow also intersects with theories about the origins of the universe. Some cosmologists have proposed that the Big Bang itself represents a kind of temporal boundary where the arrow of time was set in motion. Before the Big Bang, if such a notion even makes sense within our current understanding of physics, there may have been no distinction between past and future, no arrow of time to speak of. The emergence of time's arrow could therefore be tied to the initial conditions of the universe, with the Big Bang setting the stage for the temporal flow that we now experience. Others have speculated on the existence of multiple arrows of time, particularly in the context of the multiverse theory. If multiple universes exist, each with its own laws of physics and initial conditions, it's possible that some of these universes could have arrows of time that point in different directions, or even universes where time flows in a completely different manner from our own. In such a scenario, our experience of time as a unidirectional flow would be just one of many possibilities in a much broader multiversal landscape. While these ideas remain speculative, they highlight the profound mysteries that surround the concept of time. Time's arrow, so fundamental to our understanding of reality, is deeply connected to the physical processes that govern the universe. Yet, it also invites us to question the limits of our understanding, and to consider the possibility that time might behave differently in other contexts or other universes. As we explore these concepts, we are reminded that time, for all its familiarity, is a complex and multifaceted phenomenon. It is a dimension that we move through constantly, yet it remains elusive, defying simple explanation. The flow of time from the beginning of the universe to the present moment is not just a journey through space, but also a journey through increasing complexity and entropy, a journey that shapes the very fabric of the cosmos. In contemplating time's arrow, we are not just exploring a physical phenomenon, but also engaging with one of the deepest questions of existence. Why does time move forward? What lies at the end of time's arrow? And could time, under certain conditions, flow in a different direction? These questions continue to inspire scientists and philosophers alike, driving our search for a deeper understanding of the universe and our place within it. The arrow of time points inexorably from the past to the future, from simplicity to complexity, from order to disorder. It connects us to the very origins of the universe and propels us toward its ultimate fate. In understanding time's arrow, we gain insight not only into the nature of time itself, but also into the processes that have shaped the universe from the very beginning to the present day and beyond. As we continue to unravel the mysteries of time, we are reminded that the journey is ongoing, with each moment bringing us closer to a fuller understanding of the cosmos and the profound forces that govern it. The search for a unified theory. The universe, in all its complexity and grandeur, operates under the guidance of fundamental laws that govern everything from the tiniest particles to the largest galaxies. Yet, one of the greatest challenges in modern physics is that these laws do not seem to fully align with each other. On one hand, we have quantum mechanics, a theory that brilliantly explains the behavior of particles at the smallest scales, capturing the strange and often counterintuitive nature of the microscopic world. On the other hand, we have general relativity, Einstein's masterful theory that describes the force of gravity and the curvature of spacetime, providing a framework for understanding the cosmos on the grandest scales. However, these two pillars of modern physics, despite their individual successes, remain incompatible when it comes to describing certain extreme conditions, such as those found within black holes or the earliest moments of the Big Bang. This fundamental discord between quantum mechanics and general relativity has led physicists on a decades-long quest to develop a unified theory, one that can reconcile these two frameworks into a single, cohesive understanding of the universe. Such a theory, often referred to as a theory of everything, would provide a comprehensive description of all physical phenomena, from the interactions of subatomic particles to the dynamics of entire galaxies. One of the most promising and ambitious candidates in this search is string theory, a concept that emerged in the 1970s through the work of physicists like Leonard Susskind, among others. String theory proposes a radical departure from the traditional view of particles as point-like objects. Instead, it suggests that the fundamental building blocks of the universe are one-dimensional strings that vibrate at different frequencies. These vibrating strings are responsible for the various particles and forces we observe in the universe, with different modes of vibration corresponding to different particles, such as electrons, quarks, and even gravitons, the hypothetical particles that mediate the force of gravity. What makes string theory particularly compelling is its potential to unify all the fundamental forces of nature. In the standard model of particle physics, there are four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. While the standard model successfully unifies three of these forces, electromagnetism, strong and weak, it struggles to incorporate gravity. String theory, however, naturally includes gravity by predicting the existence of the graviton, thus offering a framework in which all forces can be described within a single theory. Moreover, string theory requires the existence of additional spatial dimensions beyond the familiar three dimensions of space and one dimension of time. These extra dimensions are compactified, meaning they are curled up so tightly that they are imperceptible at our everyday scales. The idea of extra dimensions may seem exotic, but it allows for the mathematical consistency of string theory, enabling it to avoid the inconsistencies that arise when trying to merge quantum mechanics with general relativity. However, despite its mathematical elegance and potential to unify physics, string theory is not without its challenges. One of the biggest hurdles is the lack of experimental evidence. The scales at which string theory operates are so small, many orders of magnitude smaller than anything we can currently probe with particle accelerators, that directly testing the theory remains beyond our technological capabilities. This has led some physicists to criticize string theory for being more of a mathematical framework than an empirically grounded physical theory. Nevertheless, string theory has had a profound influence on theoretical physics, leading to new insights and directions in research. It has opened up possibilities for understanding the early universe, black holes, and even the nature of spacetime itself. One of the most intriguing developments is the idea of holography, particularly the ADS-CFT correspondence proposed by Juan Maldacena in 1997. This idea suggests that a gravitational theory in a higher dimensional space can be equivalent to a quantum field theory in a lower dimensional space, providing a powerful tool for exploring the connections between gravity and quantum mechanics. While string theory continues to be a major focus of research, it is not the only approach being pursued in the search for a unified theory. Another prominent contender is loop quantum gravity, a theory that seeks to merge quantum mechanics with general relativity by taking a different approach. Developed in the 1990s by physicists such as Carlo Rovelli and Lee Smolin, loop quantum gravity does not attempt to unify all the forces of nature, but instead focuses specifically on quantizing spacetime itself. In loop quantum gravity, spacetime is not viewed as a smooth continuum, as it is in general relativity, but rather as a granular structure composed of tiny loops, or quanta, of space. These loops are incredibly small, on the order of the Planck length, which is about 10 circumflex 35 meters. According to this theory, the fabric of spacetime is woven from these loops, forming a discrete network known as a spin network. As the universe evolves, this network changes, giving rise to the familiar spacetime we experience on larger scales. One of the key successes of loop quantum gravity is its ability to address the issue of singularities, such as those found at the center of black holes or at the Big Bang. In general relativity, singularities are points where the curvature of spacetime becomes infinite, leading to a breakdown of the laws of physics. However, in loop quantum gravity, the granular structure of spacetime prevents these infinities from occurring. Instead of a singularity, loop quantum gravity suggests that there is a quantum bounce at the Planck scale, potentially offering a new perspective on the origin of the universe and the nature of black holes. Loop quantum gravity also provides a framework for understanding the thermodynamics of black holes, including the famous Hawking radiation, an effect predicted by Stephen Hawking in which black holes can emit radiation and slowly lose mass over time. By quantizing spacetime, loop quantum gravity offers a way to calculate the entropy of black holes, connecting the microstates of the spin network to the macroscopic properties of black holes, such as their temperature and entropy. However, like string theory, loop quantum gravity faces its own set of challenges. The theory is still in development, and much work remains to be done to fully understand its implications and to make predictions that can be tested experimentally. Moreover, loop quantum gravity has not yet been able to incorporate all the forces of nature, focusing primarily on gravity and the geometry of spacetime. Despite these challenges, the search for a unified theory remains one of the most important and exciting areas of research in physics. Whether through string theory, loop quantum gravity, or another yet-to-be-discovered approach, physicists are driven by the desire to understand how the universe works at its most fundamental level. This quest is not just about solving mathematical equations or finding new particles. It is about uncovering the underlying principles that govern all of reality. The search for a unified theory also has profound implications for our understanding of the universe's origins, its ultimate fate, and the very nature of existence. By reconciling quantum mechanics and general relativity, we may gain new insights into the early moments of the Big Bang, the behavior of black holes, and the fundamental structure of spacetime. These insights could, in turn, lead to new technologies and applications that we can scarcely imagine today. The search for a unified theory is not just about unifying different forces or particles. It is about finding a deeper unity that underlies the entire cosmos. It is a journey that challenges our understanding of reality, pushing the boundaries of knowledge and expanding our view of the universe. In this search, physicists are guided by the belief that there is a fundamental order to the universe, a set of principles that, once understood, will reveal the full tapestry of the cosmos. Quantum entanglement, the spooky action at the heart of reality. At the heart of quantum mechanics lies a phenomenon so strange and counterintuitive that it once led Albert Einstein to dismiss it as spooky action at a distance. This phenomenon is known as quantum entanglement, a mysterious connection between particles that defies our everyday understanding of how the universe works. Quantum entanglement suggests that two particles, no matter how far apart they are, can remain linked in such a way that the state of one particle instantly influences the state of the other, even across vast distances. This peculiar behavior challenges our notions of space, time, and the very nature of reality itself. The story of quantum entanglement begins with the development of quantum mechanics in the early 20th century. As physicists explored the behavior of particles at the smallest scales, they encountered a world where the rules of classical physics no longer applied. In the quantum realm, particles like electrons and photons don't have definite positions or velocities until they are measured. Instead, they exist in a superposition of states, where they can be in multiple places or states at once, only collapsing into a specific state when observed. In 1935, Albert Einstein, along with Boris Podolsky and Nathan Rosen, published a paper that presented what would become known as the EPR paradox. In this paper, they argued that quantum mechanics, as formulated, was incomplete because it seemed to allow for entanglement, where two particles could become linked in such a way that the state of one particle would determine the state of the other instantaneously, regardless of the distance between them. This instantaneous connection appeared to violate the principle of locality, a cornerstone of relativity theory, which asserts that information cannot travel faster than the speed of light. Einstein famously referred to this phenomenon as spooky action at a distance because it seemed to suggest that entangled particles could somehow communicate with each other instantaneously, even if they were separated by light years of space. For Einstein, this idea was deeply troubling, as it implied that quantum mechanics might be inconsistent with his theory of relativity. He believed that there must be some hidden variables, unknown factors that could explain the behavior of entangled particles without resorting to faster-than-light communication. Despite Einstein's reservations, quantum entanglement has been confirmed by numerous experiments, beginning with the groundbreaking work of physicist John Bell in the 1960s. Bell developed a theorem, now known as Bell's theorem, which provided a way to test whether the predictions of quantum mechanics were consistent with the idea of hidden variables. His work showed that no theory based on local hidden variables could reproduce all the predictions of quantum mechanics. This meant that if quantum mechanics was correct, then entanglement was real, and the spooky action Einstein had dismissed was indeed a fundamental aspect of nature. In the decades that followed, experiments were designed to test Bell's theorem, and the results consistently supported quantum mechanics. One of the most famous of these experiments was conducted by Alain Aspect and his colleagues in the early 1980s. Their work provided strong evidence that particles can indeed be entangled in such a way that the measurement of one particle's state instantaneously determines the state of the other, even when the particles are separated by significant distances. These experiments demonstrated that quantum entanglement is a real and measurable phenomenon, not just a theoretical curiosity. But what exactly is happening during entanglement? To understand this, we must delve into the quantum world where the classical concepts of space and time start to blur. When two particles become entangled, their properties become linked so that the state of one particle is directly related to the state of the other. For example, if two electrons are entangled and one is measured to have a particular spin, the other electron will instantly have the opposite spin, no matter how far apart the two particles are. This connection appears to be instantaneous, defying the limits imposed by the speed of light. Yet it does not involve any transmission of information in the classical sense, which means it doesn't violate relativity. Instead, entanglement suggests that the two particles are part of a single unified quantum system, where the properties of each particle are not individually defined until they are measured. In a sense, the two particles are not separate entities but rather different aspects of the same underlying reality. The implications of quantum entanglement are profound, challenging our understanding of the nature of reality. In the classical world, objects have properties that exist independently of whether they are observed. A tree, for example, has a certain height and color whether or not anyone is looking at it. However, in the quantum world, properties like the spin or position of a particle may not exist in a definite state until they are measured. This raises deep questions about the role of the observer in the quantum realm, and whether the act of measurement itself brings reality into existence. Quantum entanglement also suggests that the universe is more interconnected than we might have imagined. If particles can remain entangled over vast distances, then the separations we perceive in space may be less fundamental than they seem. This has led some physicists to speculate that space itself could be an emergent property of a deeper underlying quantum reality where entanglement plays a key role. In recent years, quantum entanglement has moved from the realm of abstract theory into practical applications, particularly in the field of quantum computing and quantum communication. Quantum computers, which harness the principles of quantum mechanics, have the potential to perform calculations far beyond the capabilities of classical computers. Entanglement plays a crucial role in these machines, allowing qubits, the quantum analog of classical bits, to be entangled and processed in ways that enable exponentially faster computation. Quantum communication, meanwhile, uses entanglement to create secure communication channels that are immune to eavesdropping. This is because any attempt to measure or intercept the entangled particles used in the communication would instantly disturb the system, alerting the communicating parties to the intrusion. This principle is already being used in quantum cryptography to develop secure communication networks that could one day underpin a new internet. Beyond technology, quantum entanglement continues to intrigue and inspire scientists and philosophers alike. It challenges our understanding of the universe on a fundamental level, forcing us to reconsider the nature of reality, causality, and the interconnectedness of all things. Some physicists have even explored the possibility that entanglement could be the key to understanding the fabric of spacetime itself, with research suggesting that spacetime could emerge from a network of entangled quantum states. The phenomenon of quantum entanglement has also found a place in popular culture, often portrayed as a mysterious and almost magical connection between particles. While the reality is far more complex and rooted in rigorous science, the fascination with entanglement reflects a broader curiosity about the limits of our knowledge and the nature of the universe. Einstein's initial dismissal of entanglement as spooky action at a distance reflects the profound discomfort that many scientists felt and still feel about the implications of quantum mechanics. Yet, as we continue to explore the quantum world, entanglement has emerged not as an anomaly to be dismissed, but as a fundamental feature of reality, one that challenges our most basic assumptions about how the universe works. The holographic principle. Is the universe a projection? Among the most intriguing and perplexing of these is the holographic principle, a theory that suggests our three-dimensional universe might be, in some fundamental way, a projection of information encoded on a distant two-dimensional surface. This concept, which seems to defy our everyday understanding of space and reality, emerged from the work of several visionary physicists, including Gerard T. Hooft and Leonard Susskind, who sought to reconcile the mysteries of quantum mechanics and gravity. The holographic principle finds its roots in the study of black holes, those enigmatic regions of space where gravity is so strong that not even light can escape. In the 1970s, physicist Jacob Bekenstein proposed a revolutionary idea about black holes that would later lead to the development of the holographic principle. Bekenstein suggested that the entropy of a black hole, a measure of its disorder or the number of possible microscopic configurations, was not proportional to its volume as one might expect, but rather to the area of its event horizon, the boundary beyond which nothing can return. This idea was both surprising and profound. In most physical systems, entropy scales with volume. For example, the entropy of a gas in a container is related to the amount of space the gas occupies. However, Bekenstein's proposal hinted that in the case of black holes, all the information about the matter that fell into the black hole, information that, according to quantum mechanics, should never be lost, was somehow encoded on the two-dimensional surface of the event horizon. This suggested a deeper connection between information, entropy, and geometry, one that would soon be explored further. Building on Bekenstein's work, Stephen Hawking famously showed that black holes emit radiation, now known as Hawking radiation, and can slowly lose mass and evaporate over time. This led to the so-called black hole information paradox. According to quantum mechanics, information about the state of a physical system cannot be destroyed. Yet if a black hole could evaporate completely, what would happen to the information about everything it had absorbed? Would it be lost forever, or could it somehow be preserved? In the early 1990s, Gerard T. Hooft and Leonard Susskind independently proposed a radical solution to this paradox, one that would eventually be known as the holographic principle. They suggested that all the information contained within a black hole, the complete description of every particle and every bit of energy, could be encoded on its event horizon, a two-dimensional surface. This idea was inspired by the properties of holograms, where a two-dimensional surface can store all the information needed to create a three-dimensional image. In this analogy, the three-dimensional world we perceive inside the black hole could be thought of as a projection from this two-dimensional surface. But to Hooft and Susskind's insight did not stop at black holes. They extended this idea to the entire universe, proposing that the entire three-dimensional universe could be a kind of hologram, with all the information needed to describe everything within it encoded on a distant two-dimensional boundary. This boundary, often referred to as the cosmic horizon, could be thought of as a kind of surface at the edge of the observable universe, where the information about everything inside is stored. The holographic principle suggests that the three-dimensional reality we experience, with its vast distances and complex structures, might be an emergent phenomenon, a kind of projection from this underlying two-dimensional reality. In this view, our universe is not fundamentally three-dimensional, but rather it is the result of a deeper, more fundamental two-dimensional structure that we cannot directly perceive. This idea, while deeply counterintuitive, has found support in various areas of theoretical physics. One of the most significant developments in this field came from the work of Juan Maldacena in 1997. Maldacena proposed a specific realization of the holographic principle known as the ADS-CFT correspondence, a conjecture that suggests a duality between a gravitational theory in a higher dimensional space called anti-de Sitter space, ADS, and a quantum field theory without gravity in a lower dimensional space, known as a conformal field theory, CFT. The ADS-CFT correspondence provides a concrete mathematical framework in which the holographic principle can be explored. It has allowed physicists to study complex quantum systems in terms of simpler, lower-dimensional theories, and vice versa. This duality has become a powerful tool in theoretical physics, offering new insights into black holes, quantum gravity, and the nature of spacetime itself. The holographic principle also resonates with other ideas in physics, such as the concept of emergent spacetime. In this view, spacetime itself is not a fundamental entity, but rather emerges from a deeper quantum reality. The idea that the universe could be a holographic projection from a two-dimensional surface aligns with the notion that what we perceive as space and time might arise from more fundamental underlying degrees of freedom, perhaps the entanglement of quantum states or some other quantum mechanical phenomenon. The implications of the holographic principle are both profound and unsettling. If the universe is indeed a hologram, it challenges our understanding of what it means for something to be real. The three-dimensional world we experience, with its richness and complexity, might be akin to a shadow on a wall, a projection of deeper, more fundamental information that we cannot directly access. Yet, despite its strangeness, the holographic principle provides a promising avenue for resolving some of the deepest puzzles in physics. It offers a framework for uniting quantum mechanics with general relativity, two theories that have so far resisted unification. By viewing the universe as a hologram, physicists may be able to better understand the nature of black holes, the structure of spacetime, and the origins of the universe itself. However, like many ideas at the frontier of theoretical physics, the holographic principle is still a subject of intense research and debate. While it offers a compelling vision of the universe, much remains to be understood about how this principle operates and whether it can be applied beyond the specific contexts where it has been most successful, such as in the ADS-CFT correspondence. Moreover, the holographic principle raises profound philosophical questions. If our universe is a hologram, what does that imply about our place in the cosmos? Is the universe we perceive merely an illusion, a projection of a deeper reality that we cannot fully comprehend? And if so, what does that say about the nature of consciousness, perception, and existence itself? These questions may not have easy answers, but they highlight the extraordinary nature of the holographic principle and its potential to transform our understanding of the universe. Whether or not the universe is truly a hologram, the idea forces us to think beyond the limits of our everyday experience, to consider the possibility that reality is far more complex and subtle than we ever imagined. The role of neutrinos in the early universe. In the intricate dance of particles that shaped the early universe, few are as enigmatic or as crucial as neutrinos. These nearly massless, elusive particles played a significant role in the universe's evolution, influencing the formation of structures that would eventually lead to galaxies, stars, and planets. Discovered in 1956, neutrinos have since become a key focus of study in both particle physics and cosmology, offering insights into the fundamental workings of the cosmos. Neutrinos are often described as ghostly particles because of their incredibly weak interactions with matter. Unlike protons, neutrons, and electrons, which make up the atoms in everything we see, neutrinos can pass through entire planets, stars, and even galaxies with almost no interaction. This elusive nature makes them incredibly difficult to detect. but it also allows them to provide a unique window into the processes that occurred in the universe's earliest moments. The story of neutrinos begins in the early 20th century with the study of radioactive decay. Physicists observed that in certain types of decay, specifically beta decay, energy appeared to be missing from the final state of the particles involved. According to the laws of conservation of energy, this should have been impossible, leading scientists to a conundrum. In 1930, the Austrian physicist Wolfgang Pauli proposed a solution. The missing energy was carried away by a new, as yet undiscovered particle, which he called the neutron. This particle, later renamed the neutrino by Enrico Fermi to distinguish it from the neutron, was hypothesized to have no electric charge and very little mass, making it nearly invisible to detection. It wasn't until 1956 that neutrinos were finally observed directly. American physicists Clyde Cowan and Frederick Rines conducted a groundbreaking experiment that detected neutrinos emitted from a nuclear reactor. Using a detector filled with water and a solution of cadmium chloride, they were able to capture the faint signal of neutrinos interacting with the atoms in the detector, confirming Pauli's earlier hypothesis. This discovery marked the beginning of a new era in particle physics as scientists began to explore the role of neutrinos in both the microcosm of particle interactions and the macrocosm of the universe's evolution. In the early universe, neutrinos played a crucial role during the first few seconds after the Big Bang. At that time, the universe was a hot, dense plasma of particles, with temperatures so high that even protons and neutrons could not bind together to form nuclei. Neutrinos were abundant in this primordial soup, streaming freely through the dense environment as the universe rapidly expanded and cooled. These neutrinos were produced in vast quantities during the Big Bang through interactions between other particles, such as electrons and protons. As the universe cooled, the interactions that produced neutrinos decreased, and the neutrinos began to decouple from the rest of the matter in the universe. This decoupling occurred just seconds after the Big Bang, leaving behind a relic neutrino background, analogous to the more well-known cosmic microwave background radiation. However, unlike photons, which were scattered by electrons until the universe became transparent hundreds of thousands of years later, neutrinos interacted so weakly that they essentially streamed out unimpeded from the early universe, carrying with them information about the conditions at that time. These primordial neutrinos, although difficult to detect due to their incredibly low energy, still exist today and form a cosmic neutrino background that permeates the universe. If we could detect and study these relic neutrinos, they would offer a unique glimpse into the first moments of the universe, providing clues about the conditions and processes that shaped its evolution. The influence of neutrinos on the early universe extends beyond their role as relic particles. Neutrinos also played a key part in the formation of the first atomic nuclei, a process known as Big Bang nucleosynthesis. During the first few minutes after the Big Bang, the universe cooled enough for protons and neutrons to begin fusing together to form the nuclei of light elements, such as hydrogen, helium, and small amounts of lithium. The presence of neutrinos during this period influenced the rates of these nuclear reactions, determining the abundance of these light elements in the universe. Neutrinos also had a more subtle, yet significant impact on the formation of large-scale structures in the universe. As the universe continued to expand and cool, matter began to clump together under the influence of gravity, eventually forming galaxies, clusters, and the vast cosmic web of structures we observe today. Neutrinos, with their tiny masses, contributed to this process by adding to the overall energy density of the universe. However, because they travel at nearly the speed of light, neutrinos did not clump together as easily as other, more massive particles. This means that while neutrinos contributed to the overall gravitational field, they also played a role in smoothing out some of the early density fluctuations that would later give rise to galaxies and other structures. The study of neutrinos has also led to significant discoveries about the nature of these particles themselves. Initially, neutrinos were thought to be massless, but experiments in the late 20th century revealed that neutrinos do indeed have mass, albeit extremely small. This discovery was groundbreaking because it challenged the standard model of particle physics, which could not accommodate massive neutrinos without significant modifications. The discovery that neutrinos oscillate between different types, or flavors, as they travel through space provided further evidence of their mass and opened up new avenues of research into their properties and behavior. Understanding the role of neutrinos in the early universe has important implications for our broader understanding of cosmology and particle physics. For example, the precise measurement of the cosmic neutrino background could provide constraints on various cosmological parameters, such as the density of dark matter and the rate of expansion of the universe. Additionally, studying neutrinos could offer insights into the asymmetry between matter and antimatter in the universe, a fundamental question in cosmology that remains unresolved. The exploration of neutrinos continues to be a dynamic and evolving field. Experiments around the world, such as those conducted at the Super Kamiokande detector in Japan and the Ice Cube Neutrino Observatory in Antarctica, are pushing the boundaries of our knowledge, seeking to detect neutrinos from various cosmic sources, including the Sun, supernovae, and even distant galaxies. These studies not only deepen our understanding of neutrinos themselves, but also provide valuable information about the processes occurring in some of the most extreme environments in the universe. In addition to their role in the early universe, neutrinos are also messengers from the distant cosmos. High-energy neutrinos produced by violent astrophysical processes, such as supernova explosions or the collisions of black holes, travel across vast distances with little interference, carrying with them information about the sources that produced them. Detecting and studying these cosmic neutrinos can help us understand the mechanisms behind these powerful events and the conditions in distant parts of the universe. Neutrinos also play a critical role in our understanding of fundamental physics. Their tiny masses and ability to oscillate between flavors provide clues about physics beyond the standard model, pointing to new theories that could explain the origin of their mass and their place in the hierarchy of particles. The study of neutrinos continues to challenge our understanding of the universe, pushing the limits of what we know about the most basic building blocks of reality. The Large Hadron Collider, recreating the Big Bang. Deep beneath the border between Switzerland and France lies one of humanity's most ambitious scientific endeavors, the Large Hadron Collider, LHC. This massive circular machine, stretching 27 kilometers in circumference, is the world's largest and most powerful particle accelerator. Built by CERN, the European Organization for Nuclear Research, the LHC is a marvel of modern engineering, designed to probe the deepest mysteries of the universe by recreating conditions that existed just fractions of a second after the Big Bang. By smashing particles together at incredibly high energies, the LHC allows scientists to explore the fundamental forces and particles that govern the universe, shedding light on its origins and the forces that shape it. The idea behind the LHC is simple yet profound. By accelerating protons to near the speed of light and then colliding them head-on, scientists can create an environment similar to the early universe. These collisions produce temperatures and energy densities that haven't existed since the first moments of the Big Bang, allowing physicists to study the particles and forces that emerged during that crucial time. The LHC's detectors, massive machines in their own right, are designed to capture and analyze the debris from these collisions, providing a detailed picture of the fundamental building blocks of matter. The journey to build the LHC began in the 1980s, when physicists realized that a more powerful accelerator was needed to explore the frontiers of particle physics. Existing accelerators, while impressive, lacked the energy to probe the highest energy scales predicted by theoretical models. The LHC was conceived as a tool to push these boundaries, allowing scientists to search for new particles, test predictions from the standard model of particle physics, and explore phenomena that could point to new physics beyond the standard model. One of the primary goals of the LHC was to search for the Higgs boson, a particle predicted by the standard model but never observed. The Higgs boson is associated with the Higgs field, an invisible field that permeates the universe. According to the theory, the Higgs field gives mass to elementary particles as they interact with it. The more strongly a particle interacts with the Higgs field, the more massive it becomes. Without the Higgs field and its associated boson, particles like quarks and electrons would have no mass, and the universe as we know it would not exist. The existence of the Higgs boson was first proposed in the 1960s by British physicist Peter Higgs and others, but it took nearly half a century to finally detect it. The challenge lay in the fact that the Higgs boson is incredibly massive and decays almost immediately after it is produced, making it extremely difficult to observe directly. To detect it, scientists needed an accelerator capable of producing the immense energies required to create the Higgs boson in the first place, energies that were finally within reach with the construction of the LHC. After years of planning and construction, the LHC began operations in 2008. The first few years were spent fine-tuning the machine and conducting initial experiments, but the real breakthrough came in 2012. On July 4th of that year, scientists at CERN announced that they had discovered a new particle consistent with the Higgs boson. This discovery was a monumental achievement, confirming the existence of the Higgs field and providing the final piece of the Standard Model puzzle. The announcement was met with widespread celebration in the scientific community as it validated decades of theoretical work and experimental effort. The discovery of the Higgs boson had profound implications for our understanding of the universe. By confirming the existence of the Higgs field, scientists were able to explain why elementary particles have mass and how they acquire it. This, in turn, provided insights into the mechanisms that drove the early universe's evolution, from the rapid expansion during inflation to the formation of galaxies and other structures. The Higgs boson, often dubbed the God particle, became a symbol of humanity's quest to understand the fundamental forces that govern the universe. But the work of the LHC didn't stop with the discovery of the Higgs boson. With its unparalleled ability to probe high-energy scales, the LHC continues to push the boundaries of particle physics, exploring phenomena that could point to new physics beyond the Standard Model. One area of particular interest is the search for supersymmetry, a theoretical framework that extends the Standard Model by predicting the existence of a partner particle for every known particle. Supersymmetry could help explain some of the universe's most pressing mysteries, such as the nature of dark matter, the substance that makes up most of the universe's mass but remains invisible and undetectable except through its gravitational effects. The LHC's experiments also delve into the nature of dark energy, the mysterious force driving the universe's accelerated expansion. By studying the behavior of particles and forces at high energies, scientists hope to gain insights into the fundamental nature of spacetime itself and the forces that govern its expansion. These experiments could shed light on whether dark energy is a constant property of spacetime, as suggested by the cosmological constant, or if it varies over time and space, leading to different possible fates for the universe. In addition to searching for new particles and forces, the LHC is also helping scientists understand the behavior of matter under extreme conditions. For example, by colliding heavy ions like lead at high energies, the LHC can create a state of matter known as a quark-gluon plasma. This plasma, thought to have existed just microseconds after the Big Bang, is a hot, dense soup of quarks and gluons, the fundamental constituents of protons and neutrons. By studying this exotic state of matter, scientists can learn more about the strong force, one of the four fundamental forces of nature, and how it binds quarks together to form the particles that make up atomic nuclei. The LHC's ability to recreate conditions similar to those just after the Big Bang has also provided valuable insights into the early universe's behavior. By studying the properties of particles and forces at high energies, scientists can test theoretical models of the Big Bang and its aftermath, helping to refine our understanding of how the universe evolved from a hot, dense state into the complex cosmos we observe today. This research not only deepens our understanding of the universe's origins, but also informs our knowledge of fundamental physics, guiding the development of new theories and experiments. The Large Hadron Collider represents a monumental achievement in human ingenuity and scientific collaboration. It is a testament to our collective desire to understand the universe's most profound mysteries, from the nature of matter and energy to the origins of space and time. The LHC's discoveries have already transformed our understanding of the universe, and its ongoing experiments promise to reveal even more about the fundamental forces and particles that govern reality. In the years to come, the LHC will continue to push the boundaries of what we know, exploring new energy scales and searching for evidence of new physics. It will help answer some of the most profound questions about the universe. What is dark matter? What is the nature of dark energy? Are there extra dimensions of space beyond the three we experience? Is there a deeper underlying theory that unifies all the forces of nature? The answers to these questions could revolutionize our understanding of the cosmos and our place within it. The Large Hadron Collider, by recreating the conditions of the early universe, allows us to peer back in time to the very moments after the Big Bang, when the universe was a seething cauldron of energy and particles. It connects us to the origins of everything we see around us, from the smallest particles to the largest galaxies, and reminds us of the deep connections between the forces that shape the universe and the matter that makes up our own bodies. Through the LHC, we are not just studying the universe's past, we are also exploring its future, seeking to understand the forces that will determine its ultimate fate. Whether the universe will continue to expand forever, collapse in a big crunch, or reach some other end state, depends on the fundamental properties of the particles and forces that the LHC is helping to unravel. Current Frontiers: Probing the Cosmic Dawn. The quest to understand the universe's first moments, often referred to as the cosmic dawn, is one of the most compelling and challenging pursuits in modern science. These early moments hold the keys to many of the mysteries that continue to puzzle cosmologists and physicists. Today, a range of cutting-edge experiments and observations are providing unprecedented insights into the conditions that prevailed in the universe's infancy. These efforts are pushing the boundaries of our knowledge, revealing the processes that shaped the cosmos from its birth to its current form. One of the most significant milestones in this quest came with the launch of the Planck satellite by the European Space Agency in 2009. Planck was designed to study the cosmic microwave background (CMB) radiation, the faint afterglow of the Big Bang that fills the universe. The CMB is like a snapshot of the universe when it was just 380,000 years old, a time when it had cooled enough for atoms to form, allowing light to travel freely through space for the first time. This ancient light carries with it a wealth of information about the early universe's conditions, including its temperature, density, and composition. The Planck satellite was equipped with highly sensitive instruments that measured the CMB's temperature fluctuations with unprecedented precision. Over the course of its mission, Planck mapped the CMB across the entire sky, providing the most detailed image of the early universe ever obtained. These measurements, released in a series of data releases culminating in 2013, refined our understanding of the universe's age, composition, and geometry. One of Planck's most important findings was the confirmation of the universe's age as approximately 13.8 billion years. This measurement, derived from the detailed study of the CMB's temperature fluctuations, matched closely with previous estimates but with greater precision. Planck also provided insights into the amount of ordinary matter, and dark energy in the universe, revealing that dark energy makes up about 68% of the universe's total energy content, dark matter about 27%, and ordinary matter just under 5%. In addition to refining these fundamental cosmological parameters, Planck's observations offered support for the theory of cosmic inflation, the rapid expansion of the universe in the first fraction of a second after the Big Bang. The tiny fluctuations in temperature observed by Planck are thought to be the imprints of quantum fluctuations in the very early universe, which were stretched to cosmic scales during inflation. These fluctuations eventually led to the formation of galaxies and large-scale structures, making Planck's data crucial for understanding the seeds of cosmic structure. While Planck provided a comprehensive view of the early universe, other experiments have focused on probing specific phenomena that occurred in those first moments. One such groundbreaking effort is the Event Horizon Telescope (EHT) project, which in 2019 captured the first-ever image of a black hole. Although black holes themselves are remnants of stars and not directly connected to the very earliest moments of the universe, the study of black holes offers profound insights into the nature of space, time, and gravity, fundamental aspects of the cosmos that are deeply linked to its origins. The EHT is a global collaboration that links together radio telescopes around the world to create a virtual Earth-sized telescope. This technique, known as Very Long Baseline Interferometry (VLBI), allows the EHT to achieve the resolution necessary to observe objects as small as the event horizon of a black hole, the boundary beyond which nothing can escape its gravitational pull. The black hole that the EHT imaged is located at the center of the galaxy, M87, about 55 million light-years from Earth. This supermassive black hole, with a mass several billion times that of the Sun, presented a perfect target for the EHT's observations. The image, released in April 2019, shows a bright ring of light surrounding a dark shadow, the silhouette of the event horizon. This image provided the first direct visual evidence of the existence of black holes, confirming predictions made by Einstein's theory of general relativity over a century ago. The significance of the EHT's achievement extends beyond the image itself. By studying the environment around the event horizon, scientists can test the predictions of general relativity in the most extreme conditions imaginable. The data gathered by the EHT can help answer fundamental questions about the nature of black holes, including how they grow, how they affect their surroundings, and what happens to matter and information that falls into them. These questions are intimately connected to the study of the early universe, as black holes are thought to play a key role in the formation and evolution of galaxies. Another frontier in the study of the cosmic dawn is the search for the first stars and galaxies, which formed hundreds of millions of years after the Big Bang. These objects, often referred to as population 3 stars, are believed to be the first sources of light in the universe, composed almost entirely of hydrogen and helium, the elements forged in the Big Bang. Detecting these early stars and understanding their formation is crucial for piecing together the history of the universe's evolution from a dark, featureless expanse to the rich and varied cosmos we see today. The James Webb Space Telescope, JWST, set to launch in 2021, represents the next step in this quest. JWST is designed to observe the universe in infrared light, allowing it to peer through clouds of dust and gas that obscure the view of visible light telescopes. With its powerful instruments, JWST will be able to detect the faint light from the first stars and galaxies, providing a direct look at the universe's formative years. JWST's observations will help scientists study how the first galaxies formed and evolved, how they interacted with their surroundings, and how they influenced the subsequent formation of stars and galaxies. This research will build on the foundations laid by the Hubble Space Telescope, which has already provided glimpses of galaxies that existed when the universe was less than 1 billion years old. JWST, with its greater sensitivity and resolution, will push these observations even further back in time, offering an unprecedented view of the universe's earliest epochs. The study of the cosmic dawn also involves understanding the process of reionization, which occurred several hundred million years after the Big Bang. During this period, the universe transitioned from being opaque to transparent as the first stars and galaxies emitted radiation that ionized the surrounding hydrogen gas. Reionization is a key phase in the universe's history, marking the end of the so-called Dark Ages and the beginning of the universe as we know it today. Experiments such as the Hydrogen Epoch of Reionization Array, HERA, are focused on detecting the faint signals of neutral hydrogen from this period. By mapping the distribution of hydrogen in the early universe, HERA aims to provide a detailed picture of how reionization occurred, how the first luminous objects influenced their surroundings, and how the large-scale structure of the universe began to take shape. At the same time, advancements in gravitational wave astronomy are opening new windows into the universe's first moments. The detection of gravitational waves by the LIGO and Virgo observatories has already revolutionized our understanding of cosmic events, such as black hole mergers and neutron-star collisions. In the coming years, next-generation detectors such as LISA, the Laser Interferometer Space Antenna, are expected to detect gravitational waves from even earlier in the universe's history, including signals from the Big Bang itself. These gravitational waves, often referred to as primordial gravitational waves, would provide a direct probe of the universe's first moments, offering insights into the process of cosmic inflation and the conditions that prevailed during the universe's birth. Detecting these signals would be a monumental achievement, allowing scientists to explore the universe's origins in ways that were previously unimaginable. As we continue to probe the cosmic dawn, the collaboration between observational astronomy, experimental physics, and theoretical modeling becomes ever more critical. The discoveries made by experiments like Planck, the EHT, JWST, and Hera are complemented by advances in computer simulations and theoretical work, which help to interpret the data and develop new models of the early universe. These efforts are driven by a fundamental desire to understand where we come from and how the universe came to be. By studying the first moments of the universe, we gain not only a deeper understanding of the cosmos, but also a greater appreciation for the complex interplay of forces and processes that have shaped our existence. The search for answers continues to push the boundaries of what we know, challenging our assumptions and expanding our horizons. The cosmic dawn remains one of the most tantalizing frontiers in science, a period that holds the secrets to the universe's birth and evolution. As we continue to explore this frontier, we are reminded of the vastness of the universe, the depth of its history, and the enduring mysteries that still await our discovery. Feel free to subscribe if you enjoyed this video. Thank you for staying till the end.